Today we're going to be doing an experiment that compares and contrasts simple and fractional distillation. Distillation, in essence, is a procedure that allows us to purify liquid substances. Just like we did recrystallization to purify a solid substance, we're going to be doing distillation to purify liquid substances. So, to reiterate, the objectives for today's lab would be to compare and contrast simple versus fractional distillation. And we're also going to be determining the percentage composition of a mixture using a refractometer. In today's talk, we're looking at a review of the behavior of a pure liquid. We will be looking at miscible liquids and their behavior according to Raoult's law and Dalton's law combined. We will look at boiling point diagrams for both miscible liquids as well as azeotropes, and we will show the construction of a simple versus fractional distillation graph, and we'll talk a little bit about azeotropes, which are deviations from Raoult's law. Let's just remember from when we did physical sciences way back in high school, maybe a pure liquid or pure solid substance such as ice, when we increase the temperature, we see the temperature going up, and once we get to the melting point of the substance, we see, even though we're increasing the energy output, there's no change in temperature. That's called a phase change. Once this phase change, which is melting in this case because we're increasing temperature, has been completed, we then start to see an increase in temperature as we increase the energy output. Once we get to the substance's boiling point, again we see a phase change occurring, and so we're still supplying energy, but we're not seeing or observing any increase in temperature. Again, this is a phase change, so we're moving from liquid to vapor. And then once all the molecules have been vaporized, once we increase the energy, we start to see an increase in temperature. So what is boiling? Boiling, the definition for boiling is the temperature at which the vapor pressure of the liquid equals the external or surrounding pressure. Usually this pressure is 1 atmosphere, but if we go up on top of a mountain, the pressure significantly decreases below 1 atmosphere. And so let's look at this question. Why is it when you are on a mountain cooking something, it takes longer to cook, or it doesn't cook at all? And why is it when you have a pressure cooker, it takes the same time? Well, let's think about that for a minute. If we go up a mountain, the pressure decreases, and so the liquid, which, let's say we're boiling pasta, the water doesn't get to its boiling temperature of 100 degrees Celsius. It boils at a temperature lower than that because the external pressure is lower. So the pasta doesn't reach the temperature where it cooks. The water boils, but at a lower temperature than would allow for the pasta to cook. If we had a pressure cooker, the external pressure would be high, as if we were at sea level because of the construction of the pressure cooker. And so we would have to supply the same energy as we would if we were at 1 atmosphere. And so cooking does take place under those conditions. So if we check our barometric pressure and we're not at 1 atmosphere, we would have to go to this website to get a nomograph, something called a nomograph, where there's a correction. So the boiling point observed can be set, and the pressure, the ambient pressure, can be set, and then it corrects the boiling point to if you were at 1 atmosphere. It's a very neat little tool, and if you get a chance, please visit this website so you can take a look at it. Alright, so let's talk about liquids that are miscible in each other. So they're soluble in each other. Okay? Those liquids obey Dalton's law of partial pressures, which tell us that the total pressure is equal to the partial pressure of component A plus the partial pressure of component B. Very simple. It's the sum of those two. And then Raoult's law comes into play here, because the partial pressure of A is dependent on the mole fraction of A present. So if we had a 50-50 mixture, then the partial pressure of A would be equal to the vapor pressure of pure A multiplied by the mole fraction of A, which is 0.5 in this case, 0.5. And if it's a two-component mixture, then the partial pressure of B would be the vapor pressure of pure B multiplied by the mole fraction of B, which would be 0.5. The mole fractions must add up to 1. Alright? And so in order to figure out the vapor pressure or the total pressure experienced or observed by our system, we use the combination of both Dalton's law and Raoult's law. By looking at this equation, what we notice is that if there is a lower boiling point substance, and let's say our A component boils at a lower temperature, another way of saying that is that it has a very high vapor pressure, higher than the lower volatile substance B. And so based on that information, we see that the total vapor pressure would be higher in the lower boiling point component. Let's take a look at another way of looking at this. So graphically, we see that our lower boiling point substance is plotted on the left side, and our higher boiling point substance is plotted on the right side. And the mixture, as we go from 0% of component B, let's say we are at 0.5, we see that. So distillation is a process that's used to separate liquid substances based on their differences in boiling point. Or another way of saying that is the differences in ease of vaporization. As the mixture is heated, the temperature increases and the lower boiling point component vaporizes. When this is happening, it's like a phase change for a pure liquid, and so no change in temperature is noticed until most of the vapor of the volatile substance is boiled off. Alright? And what happens to the other component? Well, let's think about that. We have a vial with our liquid, and as one component boils off, condenses, and is collected, what happens to the liquid in the boiling pot? It becomes enriched in the other component. Here we have a diagram of a simple distillation apparatus, and what we see happening is that we're boiling the liquid and the vapor comes off. It goes through the condenser and turns back to liquid, but it's enriched in the lower boiling point component, as we talked about before. And what's happening in here is that this mixture is getting enriched in the higher boiling point component. And so we have separation, lower boiling point component, higher boiling point component. Okay, so this is the temperature composition diagram. If we have a component with, let's say, 30% A, 70% B, which would be our W, we increase the temperature, and what we see happening is that once the temperature reaches the liquid curve, which happens if we draw a horizontal line across, which happens at 130 degrees Celsius, is that it starts to boil. So when you draw a vertical line from your mixture composition to the liquid line in this diagram, that's when the liquid boils. So by extending a horizontal line across to meet the vapor line, that tells us the composition of the vapor that's in equilibrium with this liquid that's boiling, which is our Y. Alright, and to find the composition, we draw a vertical line down to the x-axis, and that gives us Z, and that's telling us that our condensate is now 70% A and 30% B. So it's enriched in the lower boiling point component, A. The boiling point of pure A, we can read this from the y-axis over here, which looks like 70, 80, 90, 100, so that's 90 degrees Celsius. And the boiling point of pure B looks like, if we extend the line over on this side, it might be 150, 160, 170 degrees Celsius. Okay, so this line that connects the vapor that's in equilibrium with the liquid is called a tie line, and this whole process of boiling, liquid turning to vapor, vapor condensing into liquid again, is called one theoretical plate. Based upon the previous slide, you should be able to identify the boiling point of pure A, the boiling point of pure B, and we talked about the boiling point of the solution with the composition of 30% B. That seemed to be about 130 degrees Celsius. And if we extend a horizontal line from the liquid part of the vapor curve to the vapor part of the curve, we see that, and then we draw a vertical line down to the x-axis, it gets enriched in component A to 70% A and 30% B. With fractional distillation, we not only have one theoretical plate, but several. And how we achieve fractional distillation is by placing a material with a high surface area, such as a steel sponge, into a part of the distillation apparatus. So what's happening is that we have vaporization occurring on the sponge, as well as condensation back into the boiling flask, and then the process is repeated a few times. That allows for more separation of the different constituents. But then I remembered that people had trouble seeing when the drop came out, so I don't want them to actually attach anything on this side.
So,
They'll collect in a beaker.
okay.
Because they couldn't tell if this was a drop, if there was a drop in there.
Okay.
It was hard, with condensation happening. It gets cloudy in here.
Okay.
Okay, so you can take it apart.
So I'm just gonna be part of me putting that together.
Yeah.
And, like, just setting it.
Is there a rubber in here?
You're right.
A rubber, an O-ring, yeah. Okay, so go ahead and take it apart. And we want it to be hooked up with a hot plate. And we're using one of these. And do their poses. Here we see that if we start with L1, we have to go through 1, 2, 3, 4, and then a fifth theoretical plate if we were to achieve 100% A. Hopefully you had a chance to visit this website to see how to set up your distillation apparatus. Here we are showing the graph that you will need to construct for your lab report. In the lab, you want to collect temperature versus number of drops of distillate. Okay, and what you should see is that with fractional distillation, you will see more of a straight line region when the two fractions are coming off, or the two components are coming off. Whereas with simple distillation, it's more of one continuous upward sloping line.